to my group mates, thesis advisor, especially to our panels who are present today, good day. Thank you very much indeed for letting us present what we have done over the past few months. To begin with, I would like to introduce myself. My name is Robbie Carlina Aquino. I was assigned to discuss Chapter 1 Introduction, Parts 1.1 and 1.2, General and Specific Objectives, as well as Chapter 4, Part 4.1, Total Coconuts Recording Samples. Our thesis, Coconut Classification System using Microcomputer and Naive-based algorithm via sound acquisition, gave us the opportunity to study coconuts into details. As your presenter, I will highlight on the most important points for the introduction part. In the first slide, it talks about how important the coconut in our daily lives, for it gives a lot of benefits in both farmers and consumers. Research also mentioned that it is usable for human needs such as shelter, food, and clothing. In addition, this slide also mentions the byproduct of coconut kernel, such as coconut milk, coconut oil, coconut flour, coconut candy, jelly, shredded coconut, and coconut butter. Now, when it comes to coconut water, it produces natural energy drink based on the studies full of electrolytes, emergency hydration fluid, and coconut vinegar. As for the last slide on the introduction, the conventional way of coconut farmers in identifying the type of coconut after harvesting is by flicking each coconut shell and relying on the sound that was produced after flickering. The problem in their conventional way is when it is time for harvest, coconut farmers flick each coconut in bulk, in which it leads to less accurate classification. Going to the next part, 1.2.1, General Objectives under 1.2 Objective of the project, it only states that this study aims to present a design of a portable system that can be used to classify coconuts into one of the three types, specifically as buko, nyog, or makapuno, via sound acquisition for commercial use. Moreover, this slide 1.2.2 specific objectives, still under the objective of the project, focuses only on the above-mentioned specific objectives of the study, such as to develop a handheld device with audio sampling and fast Fourier transform algorithm, to gather and record sound to be used for training datasets produced from Buko, Nyog, and Makapuno, to determine which algorithm will be used for the accuracy of the coconut classifying device, to integrate and determine algorithm and the coconut classifying device, and to test and evaluate the integrated coconut classifying device.
I'm here to discuss the significance of the project and scope and delimitation. Significance of the project to the coconut businesses and industries is that it involves a large number of coconuts. The portability that will create of this device is that it will determine the type of coconut in real time and of course with high accuracy. This also allows the person to know the type of coconut without the knowledge of conventional way. For the coconut farmers, we know that the coconut farmers have the knowledge of the conventional way of classifying coconut by experience and it takes time to gain it. The result of this device benefits them with or without the experience to classify coconuts without taking too much of their time, since they are so-called expert in the field of the said product. To future readers, researchers, and students, this will develop their interest in the application of signal processing, which will help them to be efficient in their daily lives. Scope and delimitation. Our project will focus on classifying a coconut, which will be categorized into three types: buko, nyog, and makapuno. In line with this, the device will not detect if the buko is malauhog, malatenga, or malakanin.
The next chapter is the Chapter 2 Review of Related Literature. Introduction to Literature Review. Automated coconut identifier has been used for different methods to ensure that the coconut is identified accurately. An application involves the use of the sound sensor module in the system. Innovation is progressing in the course of time. This project develops an algorithm that can identify types of coconut according to the different sound characteristics of each type.
So I will talk about Chapter 2, Literature Review and Framework of the project. In the introduction to literature review, in the first paragraph, it talks about the different method to identify the each type of coconut. So in this project, develops an algorithm that that can identify types of coconut according to the different sound characteristic of each type. Of literature review. Measurement of young coconut, Cocos nucifera, maturity by sound waves, is a study from University of the Philippines Quality Partners Company with the following authors: Itlora Gatchalian, Sonia Y. De Leon, Toshi Masayano. So in this project, they made a device called Soundbox. The purpose of Soundbox is, is to record the sound of tapped coconut, which is to identify the three types or the three stages of coconut, which is malauhog, malakani, and malakatad. So they record sound sound samples, then they converted into digital with 12-bit ADC and sampling rate of 21 kHz using fast Fourier transform. Result of literature review. The design of coconut maturity prediction device with acoustic frequency detection using naive-Bayes method-based microcontroller. It's a study from University of Tronuyo, Madura from East Province, Indonesia, with the following authors: Diana Ramwati, Haryanto Arianto, Farius Sakaria. Identifying the age of coconut can be determined by its knocking with shell. The appearance of coconut, it is inaccurate to distinguish its maturity. So they in this project they perform a preliminary study to identify the coconut using acoustic frequency from knocking the coconut shell. The equipment used to record the knocking sound of coconut consists of knocking tools, stethoscope diaphragm, noise sensor, microcontroller, LED, and laptop. To record, the coconut is placed in the middle of knocking tool and stethoscope diagram, which is connected to MAX 9814 sound sensor module with Arduino Due. The sound will caught by two listening device, which is stethoscope diagram and sound sensor. Then it will be sampled to 1000 Hz by Arduino to convert into digital frequency. To get the precise frequency, digital filter will be used to minimize the noise signals. And the average knocking frequency will be saved to SD memory card and will serve as a training dataset for the coconut maturity prediction with the application of acoustic detector with name-based method using laptop. So the formula for the probability approach is in the equation below. So this is the formula they use in the making their project. So if the if the data is in numbers, the Gaussian dispersion technique will be used to calculate its probability value. The, the formulation for the Gaussian dispersion technique is stated below. So this is the formula they use for Gaussian dispersion. So in this table, uh, you will see that as a result of coconut maturity prediction device with acoustic frequency detection using Ney-based method. So which is our 24 coconut training sample data and 20 coconut test sample data that contains different. This, this result generated 80% success rate on maturity prediction. So in this table, you will see the F1, F2, F3 of are the range or the value of each data. So the the S, which is identified as oval long shape, and its circumference is medium. Uh, the D meaning is fairly mature, and M is the meaning of young. T stands for old coconut. B identified as big circumference and length, or it is a big size. So this is the 24 training data of coconut maturity prediction system. The table 2 shows the test data of coconut maturity, which is consists of small size K, which is identified as a round shape, and its circumference is small. Medium size S, which is identified as long oval shape, and its circumference is medium. And big size B is identified as big circumference and length, while the maturity level consists of M, fairly matured D, and old stands for T, coconut.
The next study is the coconut fruit maturity classification using Logic, a study from De La Salle University, Manila, Philippines, with the following authors: Havel, Bandala, Salvador Jr., and etc. This study from De La Salle University presented a MATLAB simulation to classify the coconut fruit as malauhog, malakanin, and malakatad. They define malauhog as a very soft and jelly-like meat and with green husk. For malakanin, a white firm opaque coconut meat and yellowish husk. And for malakatad, a very much firmer coconut meat with brownish husk. The process will start from tapping and getting the input data, P sound for sound, and P brown for image color from the coconut. They use microphone and camera as sensors. Then, it will be processed to compute for its brown percentage in color, and for the sound, it will compute the average of the normalized spectral magnitude. Then, for the output of their simulation, it will be determined through using the fuzzy inference system. So this is their presentation on how they classify it. So the fuzzy logic approach will get the output by referring to this table, which have P brown and P sound as input and malauhog, malakanin, and malakatad as output. For example, if P brown is low and P sound is low, then the output is malauhog. At the conclusion of the study of simulation, this study is able to determine the coconut maturity based on color and sound. In addition, the fuzzy logic approach is an effective algorithm to use for a classification system. The researchers of this study recommends to have an actual coconut fruit in testing because it is only a simulation. The next study is MATLAB-based coconut maturity classifier using audio and image processing. A study from Asia Pacific College, Makati, Philippines. With the following authors, Samaniego Jr., Fajardo, Mojica, and Yokoko. This is the actual picture of their device that can identify the maturity of coconut with 4 categories, which are mucus-like malauhog, cooked rice-like malakanin, leather-like malakatad, and germination. The device is a box and has a dimension of 45.72 by 39.37 by 39.37 centimeters. The coconut will be placed inside the device to determine the age. For this study, there are 2 ways of classifying the maturity of coconut in the testing box, which can be obtained by sound or thermal. For the sound, DC motor is attached inside the device along with the mic to record the sound of tapping the coconut. The testing box is acoustically insulated to prevent the noise outside. They use a foam. The recorded sound will be converted to digital using fast Fourier transform and will undergo to amplification by 10 dB to avoid distortion. And it will be filtered using the Butterworth low-pass filter. For the thermal, 8x8 AMG 8833 thermal camera is attached inside the device to measure temperature of coconut. The camera has 64 pixels. Each pixel detects different value of temperature. The average of all pixels will be calculated to determine the heat content of the coconut. In result, the accuracy of the sound for classifying the coconut is 93.33%, meaning classifying the coconut with sound is more accurate than measuring its heat content. This is Chapter 2 conclusion and framework of the project. This is our representation of conceptual framework of the design project, which includes our input, process, and output. In Figure 2, it shows the conceptual framework of the coconut classifier. The proponent's aim is to classify the coconut into 3 types, which are buko, nyog, and makapuno. The presented studies show that the age of coconut has a relationship with the frequency produced by knocking and with the color of the outer shell. The proponents will choose a process that has a high accuracy for classifying the coconut, which is audio processing. The coconut itself is the input of the design project. To identify the type of coconut, the device will have a mechanical tapping tool using a solenoid and microphone that will capture the sound frequency. The captured sound frequency will be converted to digital by a microprocessor to extract the characteristics of coconut. To identify the type of coconut, machine learning will be implemented as a classifier to sort the types of coconut. Also, the device will be trained in the noisy environment to not affect its highest accuracy, which is less than 100%. And that is all for our chapter 2.
Before we proceed in discussing Chapter 3, please let us show you our interview with Mr. Eduardo Aquino Jr., also known as Kuya Onyo. He is a coconut farmer and vendor in Meycauayan, Bulacan.
So, good day. I'm here with Kuya Unyo, one of the farmer and coconut vendor here in May Kawayan, Bulacan. So, Kuya Unyo, my first question is, paano yung method niyo sa pag-identify ng tatlong fruit na nasabi ko kanina, which is yung buko, nyog, saka makapuno?
Ano lang yun, pagka yung inom siya kasi, pag ang buko, pag inom siya, magaang, ay mabigat.
Opo.
Pero pagka yung magkaan siya ng nyug, magaang na siya.
Opo.
Wala silang pinagkaiba ng makapuno at ng nyug
Opo.
sa dalawa. Pero sa buko, meron silang pagkakaiba. Pag pinitik mo siya na sa dito, magbabibrate ang tubig.
Opo.
Yun ang ano yan. Tapos yung sa device na ginagawa nyo,
Opo.
mas maganda kasi mapapadali siya eh. Kung
Opo.
lalo pag na-develop ng gusto yun. Yun ang ano niya. Yun ang kagandahan sa in-invento yung device.
Tapos kuya, ano pa lang, follow up ko lang, balisan ba dapat pinipitik yung ano, yung
Yung pinaka...
yung mga
Coconut.
yung coconut mismo?
Dito talaga. Sa pinaka niya dito. Yan talaga.
Sa
Kasi dito
pinaka-lower
pinakababa niya. Kasi ito pinakamanipis na balat eh.
Opo.
Pag dito kasi makapal siya.
Ayun.
Ito manipis.
Kuya, can you have a sample ng ano? May mga nadiyak niya na kanina. Like yung ano.
Ano?
Oo nga. Mas
Manipis siya. Tingnan mo. At babalat tayo na isa, mas makapal yung pinakababa.
ayun.
Diba?
Ayun,
Makapal siya.
sa taas.
Dito
Mas
manipis.
Ayun.
Mm.
So talagang dyan niya pinipitik yan kuya.
Dito sa
pinakapuwetan.
pinakababa.
Pinakaiba.
Pinakababa siya.
Tapos same, yung sa pagkakaiba naman ng ano kuya, ng netong nyog na may balat na dala-dala nyo. Tapos doon sa buko, ano yung parang, paano nyo siya na-determine kahit may balat pa siya?
Ano? Ito, di ba? Para siyang kahoy na.
Opo.
Kahoy ng dating ang tunog niya. Hindi tulad dito, malambot yung tunog.
Malambot yun.
Malambot na malambot.
Ayun.
Tinaano niya. Pagka nagtetesting talaga sa pinakababa.
Pinakababa. Tapos kaya yung sa ano, yung di ba sinasabi mo kanina about doon sa ano, yung mga matatandang, yung mga talagang bihasa na sa pag ano ng buko, nyog tsaka makapuno. Ano yung paano sila tumitingin sa puno?
Sa puno, yung pinakataas, tubig pa yan. Malauhog yan. Tumunod, medyo, ano yan, tagok.
Opo.
Kalahati, nilaman kate, wala. Tapos pinakababa, ano siya, nyug na siya.
Nyog na.
Mm,
Pero yung
Binhi na siya pagka ano.
pero yung makapuno, kuya, sa pag-determine naman ng makapuno sa kanyog, halos kasi
Walang
may
pinakaiba.
nakausap kami na farmer na ano, nitong isang farmer na nakausap din namin via Facebook din. Ang sabi niya, wala daw pagkakaiba yung nyog saka yung makapuno.
Wala.
Pero malalaman lang daw yun pagka binalatan,
Binuksan na.
tapos pinitik
Mm.
agad. Doon daw nalalaman kung
Sa
makapuno
pitik,
siya o
tsaka
hindi.
sa alog.
Ayun.
Dalawa yun eh. Kung isang ano, pagbalat na siya, yung brown na siya,
Opo.
pag inalog mo siya, masyadong maraming tubig, panggata yun.
Ayun.
Pero yung isa, pag ginano mo siya, parang wala siyang alog,
Oh.
makapuno yun. Kasi ang makapuno, ang pinakatubig niya, nagiging ano siya, jelly.
Opo.
Nagiging ano siya, jelly talaga siya, yung pinaka sa loob niya.
Opo.
Kaya pagka binuksan mo siyang ganun, para siyang unti-unting bumabagsak.
Ayun.
Kasi jelly siya eh. Hindi katulad ng nyug, tubig.
tubig ang laman. Tapos pagka pinitik mo, parang walang laman yung loob ng
Oo.
makapuno dito.
Oo.
Ayun. So, thank you very much, Kuya Unyo. And
Mm.
thank you sa time para sa sa napakalaking tulong para sa project namin
Pero malaking bagay, ma-develop yung parang gusto yan.
Ayun.
Malaking tulong sa farmers para pag na-develop siya.
Sige, dito
Sa
sa
pag-unlad ng bansa natin yan, di ba?
tama-tama since coconut tayo isa tayo sa pinakamalaking supplier ng coconut
Oo.
Sabi mo nga dahil common yung kahit saan ka makita dito sa Pilipinas, may puno ng
Hindi,
ng
sa abroad doon, kahit pumunta ka sa kung saan dito, sa bansa natin, mas kinaangkatan pa tayo ng ibang bansa.
yan nga po.
Oo. Kaya talaga, kinukuha nila.
Nagsusupply tayo sa
Sa tayo
kanila.
nagsusupply.
So, bawal mo na shake hands, kuya. Thank you very much.
Okay.
In this video, I will present about 3.1 project design. So, the classification system uses different acoustic properties for each type of coconut involved in this study. Each type requires at least 30 samples to collect and record its sound and obtain its fundamental frequency using fast Fourier transform algorithm. Once the fundamental frequency is obtained, it will be then used as a training data or a test data for the device. Once all the test data is obtained, it will be categorized as class 0 for buko, class 1 for nyog, and class 2 for makapuno. After this, it will be then used for simulation using MATLAB Classification Learner app to recognize which machine learning algorithm is to be implemented to the device. Once the machine learning is known and it's already implemented to the device, it can now function and process the information and decide which coconut type resembles the data, which is either buko, nyog, or makapuno. Next is we have the input process output diagram. First is the input or the industry standard use. By understanding the farmer's perspective on segregating the coconut through sound and coconut varieties and their specific acoustic properties and the prototype design. For the process, we have the hardware and software implementation, recording of different coconut varieties, and processing of sound wave through fast Fourier transform, and choosing the right machine learning algorithm through MATLAB simulation. The output is the ranges of frequency from different varieties and the actual device, which is portable coconut classification device. Next is 3.1.1, the industry standards use. Farmers' perspective is very important in this study since they are the one who knows how to classify the coconut using sounds. In this scenario, we have a pair of buko and nyog with husk. Then the farmer will tap it and the farmer will now conclude based on the sound produced by tapping it, which is either buko or nyog. Next is a pair of the husk, nyog, and makapuno, meaning walang balat na nyog and makapuno in Tagalog, and tapping it, and farmer's conclusion based on the sound produced by tapping it, which is either nyog or makapuno. Next, the 3.1.2, which is design constraints. When the device is built and functionable, it will undergo a preliminary testing and proper data acquisition to acquire the accurate sound frequency for each sample of coconut. The scale of the datasets required to obtain much higher frequency is from low to medium scale. As for the hardware, it requires a large memory to store the data. Next is the design trade-offs. The device cannot provide 100% accuracy due to the following factors. First is the outside noise. Second is the clatter sound produced by the solenoid. However, the solutions for this is by trimming the sound which is programmed in the device. So, for nyog and bakapuno, it is needed to be dehusked before the device can identify it as nyog and bakapuno. As one of the farmers that we've talked said that for them to be able to identify the nyog and bakapuno, they need to dehusk it and tap it to identify it whether it is a nyog or a makapuno.
Project development and implementation. To make this project feasible, it requires a hardware component such as microphone that will act as a sensor, low-powered mechanical solenoid that will act as a knocking tool, and Raspberry Pi Zero that will process the data and implement the desired algorithm. For the software, it requires a program that has the capability to run the hardware and can be applied in very in every condition that is needed to be followed to make the system working. In this study, the programming language that we'll use is Python and will implement the naive-Bayes method, a machine learning algorithm that compares the data according to its class or probability given in the training data that is stored in the memory.
Chapter 3 System Block Diagram. In the next figure, it illustrates the block diagram of a coconut classifier. The first block is a mechanical solenoid which is used to tap or knock the coconut to produce sound, which can be captured and sampled by microphone sensor. The FFT spectrum analysis is used to determine its fundamental frequency of sound when the fundamental frequency has been determined on each coconut samples. The data will be pre-processed to organize and label the data, which will be used by naive-Bayes algorithm to determine the coconut to its acoustical property. And this is the system block diagram of coconut classification system. First is solenoid mechanical tapping, audio recording, FFT spectrum analysis, data pre-processing, naive-Bayes classifier, and lastly the coconut classification. Chapter 3 Schematic Diagram. In the next figure shows the full schematic diagram of the coconut classifier system, which includes the wiring of linear solenoid to microcomputer, mini microphone, and LED indicators. The battery with constant voltage that will power all the components of the device. And this is the schematic diagram of a coconut classification system. On the left bottom corner, we have three LED indicators, and on the top, which has a USB 2.0 mini microphone, and we use micro USB OTG cable. And on the top right corner, which is the linear solenoid system that will knock the coconut, and lastly the battery, which has 5 volts and 12,000 milliamp battery capacity. Chapter 3, Sound Acquisition and Processing. In this system, we use USB microphone. It is small microphone with no drivers required. Just a typical plug and play. In terms of its level of performance, this microphone is capable of digital sound processing, which is highly compatible to Raspberry Pi controller that we use. Also, for portability purposes, we need a microphone that is small in size and efficient on capturing sound. The image above shows the sound frequency of coconuts in terms of time domain and frequency domain. The graph in frequency domain is one that we will apply to find the value of highest frequency.
Good day, my name is Ratal C. Rasusta from Group 1 Coconut Classification System. So, I will talk about the Chapter 3, project Design and Methodology. Uh, Microcomputer. Microcomputer technology evolves as time goes by. The size of computer becomes smaller yet, with the increasing speed of processor. The Raspberry Pi Zero is a microcomputer that has 1 GHz single-core CPU with 500 megabytes of RAM. A smaller version of Raspberry Pi Model A Plus also has the same specification and function with Raspberry Pi Zero. We use the Raspberry Pi Zero because it's more advantage over the microcontroller. It is greatly used for digital sound processing, and it can be applied in machine learning. With machine learning, the system will have high accuracy that it can learn from the inputs. This means that this microcomputer has its own fast-fourier libraries and has its own machine learning libraries. So in this video, you will see the Raspberry Pi Zero that will be used in the coconut classification system. So LED indicator. LEDs are installed in the system for the identification of coconut. The microcomputer, which is Raspberry Pi, will send a signal in which LED will activate after processing the sound of the coconut. The green is for buko, the white is for nyog, and the red is for kapuno. Uh, this figure represents the legend of LED indicators. So, chassis design. Uh, in this project, we design a gun type chassis for portability uses. This, the design can fit all the components that we use in our system, which is Raspberry Pi, microphone, solenoid, LED, push button switch, and battery. We use Raspberry Pi as a microcomputer, microphone to gather the sound, mechanical solenoid for knocking the fruit, push button switch to trigger solenoid, while the battery is supplied for Raspberry Pi. And also we use the LED diode to identify the types of coconut. So you can see in this picture our computerized sketch for design for so in this figure In the top view of a gun type, the LED was placed. So in the white diode represent the buko, the green diode uh, LED diode will present the buko, and the red LED diode represent the makapuno. So in a front view of a chassis design, you will see a solenoid and microphone are placed in front to easily aim each coconut. So you will see the microphone is above, and while the solenoids is below. So inside view, push button switch serves a trigger to knock the coconut. You will see this gun type model. So in the back view, the micro USB was placed on. Micro USB is used for charging battery.
In this video, I will present about on how we chose a machine learning algorithm for our device. As you can see, the lower left part in our plot is the blue dot here is the class 0 type of samples, which is buko. The red part in the middle part of our plot is class 1 type of samples, which is nyog, both with husk and the husk. And the yellow dots here in the upper part of our plot is class 2 type of our samples, which is makapuno. The plot that you can see here is a Gaussian naive-Bayes model with an accuracy of 95.6% and a total misclassification cost of 2. And take note that the data that we use in our simulation is the actual recorded data for our 3 samples, which is buko, nyog, and makapuno. And also, we obtained this plot using MATLAB Classification Learner app. Next is the kernel naive-Bayes model with an accuracy of 95.6% and a total of misclassification costs of 2. Next is a fine tree with an accuracy of 93.3% and a total misclassification cost of 3. Next is the medium tree with an accuracy of 93.3% and a total misclassification cost of 3. And last is the coarse tree model with an accuracy of 93.3% with a total misclassification cost of 3. In summary, both classification of naive-Bayes, which is Gaussian naive-Bayes and kernel naive-Bayes, yields an accuracy of 95.6% with a total misclassification cost of 2. But in our case, we cannot choose both and we stick to Gaussian naive-Bayes algorithm. And also, naive-Bayes and decision tree are machine learning algorithms that can be used or that requires a small number of datasets.
Software flowchart. The software flowchart shows the process of determining the type of coconut via machine learning using the fast Fourier transform, spectral analysis, and decision tree. To initiate the process, the first step is to press the button to trigger its linear motion solenoid and capture its sound by electret microphone breakout. Once the sound is captured, it will be sampled by electret microphone breakout and will undergo to the fast Fourier transform to determine the fundamental frequency So it will be pre-processed to prepare the data to its next two conditions. If the process is not decision tree, then the new training data will store to the memory and will separate data according to its class of then summarize data sets. The Gaussian probability function will calculate the probability of each data according to its class. Once the dataset has been verified, then it will update the classifier and will return into the recording coconut frequency to, to test the device to capture a new dataset for training data. If the condition is testing decision tree model, then the data will proceed to decision tree classifier model and match it with the new training data available in the system. And we'll choose one of classification according to its type. And LED will turn on to its corresponding result.
Chapter 3 Functionality Testing. The device in the figure was used to classify the types of coconut. In using the device, the user must aim for the top of part of the coconut. The button should be pressed to trigger the solenoid and knock the coconut. The sound captured by the mic processed by the microcomputer, and finally, the type of coconut will be displayed through LED indicators.
In this video, I will present about calibration. Before we proceed in the calibration part, first is we need to understand that a coconut with husk has a three different regions, which is upper region, middle region, and lower region. The following are the steps for calibrating our device. First is to acquire 30 samples for each type of coconut. The second is tap on 3 regions of coconut. And third is to tabulate the data obtained from the samples for validation. And fourth is opening the coconut. Once the tapping on all samples are done, we need to tabulate the recorded sound data for observing on which region that we can obtain a much better frequency. And take note that all class 2 samples which is makapuno are dehusked. As a result, the lower region of the coconut in class 0 and class 1 with husk has the best frequency that can be obtained since it has the thinnest husk. In classes 1 and 2 without husk, the frequency on the entire region is almost the same since the kernel of both class 1 and class 2 is almost evenly distributed on their shell coverings.
In this video, we will show you on how the device works. As we can see, the device has a gun-like structure for portability purposes. The way the device works is to be pointed directly at the coconut and push the trigger-like button to activate the solenoid knocking tool, which produces a sound, and the microphone will capture it. Once the sound is already captured, the computer on board will process it and will produce an indicator output which corresponds depending on the type of coconut that is being sampled.
I would like to present to you this table which shows the total samples of each coconut. In this project, we have 90 samples to train the device. Each type has its own range. The frequency of each type is shown on the table of calibration part.
In this video, I will present about 4.2 functionality results. Functionality results contains process of testing, sampling results, test results for random samples, and device accuracy. The first step of testing is to acquire another 15 samples for each type by contacting all available suppliers of coconuts to prepare all samples needed for testing. Second step is to prepare the device, making sure that the device is well calibrated and fully charged as well. The third step is contacting a coconut farmer/vendor. Coconut vendor, also known as magubuko, will help us to open the coconut once it was classified by the device. And the last step is the actual testing of the device. Once all the samples are acquired and the vendor is already available, we can now conduct a device testing. For the sampling results, we have the frequency range and its specific device indicator. For buko, the frequency range from 1300 to 1999 Hz, and the device indicator is color green LED, while nyog ranges from 2000 to 2699, and the device indicator is color white LED. And for makapuno, frequency ranges from 2700 to 3399 Hz, and the device indicator is color red LED. The test results for random samples. For random samples, we have 15 buko as well as nyog and makapuno with a total random samples of 45. The number of correct classifications are 42, while the number of incorrect classifications are 3. For the device accuracy, we have to divide the total number of correct classifications over total number of samples times 100%. For this, we have obtained at 93.33% of accuracy for the device. On the next video, we will show you on how our device works with the actual coconut samples involved together with Kuya Unyo.
Aray kang makikilapit ka para makita yung ilaw.
Ikaw daw.
Makikita mo.
Eh.
Okay, kaya buko, pakibuksan po.
Oops. Ito.
So,
Malambot siya pagka ano.
ayun.
Oops. Pero pagka gusto mo, pumunta ka lang doon, walang problema doon. Sa alam mo na yung bahay namin.
Ay, yes sir.
Oo, kung tungkol sa ano, punta ka lang doon.
Sige
Kasi
po.
nandun naman ako, mga bandang alas 6 ng hapon.
Hapon.
Nandun ako.
Bali, hapon, hanggang hapon.
Kaya kahit anong sabihin mo doon, kaibigan ako ni tatay mo. Walang problema doon.
Sige.
Hindi naman yung mga anak kong babae.
Tsaka yung mga, ayun, pabiyak na lang kaya. Ayan. So you can see sa ano natin, tama yung naging classification ng device natin, which is buko yung naging detection ng device natin. So next is okay, then ito kay Kuya. So Kaya pwedeng makita siya yung matatanggal mo yung pinaka-shell niya. I mean yung parang mababalatan mo siya.
Ay, gigian mo ang ganun.
Parang makita lang yung talagang yung naman.
Hindi, sasalin natin siya para ano.
Sasalin natin. Parang mawala yung sabaw.
Hmm.
Sige. Kahit i-ano mo na lang yung sabaw, kuya, kasi hindi na namin siya.
Hindi na ano. Tapon na lang natin kasi maasim yung sabaw niyan.
Yun nga po.
Pag ano kasi ganyan na ano siya, binhi na siya eh. Mga ilang buwan lang talaga magkaroon siya ng sanga rito.
Ay, okay. At the same time, pwede na rin siya panggataan, kuya.
Oo, panggata na siya.
Ayun. Ayan. So, as you can see, na-detect ng device natin na nyog talaga yung laman nung mismong coconut natin. So, next testing, okay na. Okay. So, kuya, pakiyan po. Yun. Okay, so kahit dehas na yung coconut, tama pa din yung naging classification ng device natin, which is nyog. Then, last. So yun, nakapuno. Nakapuno yan.
Kuha ka na ako sa sakitan.
So yun. So yan ang structure rin ng makapuno. As you can see, mas makapal yung kernel niya sa nyog. And medyo may pagka-gelatinous yung pinaka structure niya sa loob, yung pinaka kernel niya mismo. So, okay.
Hi, I'm Ron P. Santos. I'm here to discuss the power consumption and the unit price. Power consumption. Why do we need to compute the power consumption? We need to compute the power consumption to obtain our desired operational time for this project, which is 8 hours. Raspberry Pi Zero. So the first device that we will compute the power consumption is Raspberry Pi Zero. So Raspberry Pi Zero has the voltage rating of 5.83 volts, current rating of 120 milliamperes, power rating of 0.7 watts, hours of use 8 hours. So to compute the power consumption, power rating multiplied to the hours of use, so we will have 5.6 watt hour. Electric solenoid. Electric solenoid has the voltage rating of 6 volts, current rating of 300 milliamperes, power rating of 1.8 watts, hours of use 8 hours. Therefore, our power consumption for electric solenoid is 14.4 watt hour. Adafruit electric microphone. Adafruit electric microphone has a voltage rating of 3.6 volts, current rating of 100 mA, power rating of 0.36 watts, hours of use 8 hours. Therefore, the power consumption of this device is 2.88 watt-hour. LED. LED has the voltage rating of 1.8 volts, current rating of 54 mA, and power rating of 97.2 milliwatts. Hours of use is 8 hours. Therefore, the power consumption will be equal to 0.778 watt-hour for LED. So to get the total power consumption, we will get the sum of the power consumption of each device. So we will have 23.66 watt-hour. So to get the life capacity of the battery, we will divide 23.66 watt-hour to the input voltage of the battery, which is 5 volts. So we will have 5,000 milliampere hour. So in the market, there is 10,000 milliampere hour. Instead of using 5,000 milliampere hour, we will use 10,000 milliampere hour. Therefore, the device will have the operational time of no more than 16 hours. Unit price. So let's talk about the prices of each equipment that we use to make this project. One Raspberry Pi Zero has a price of 1,499 pesos. One electric solenoid has a price of 350 pesos. One HC981 chassis has a price of 50 pesos. One lithium battery has a price of 245 pesos. One electric microphone has a price of 79 pesos. One micro switch with roller has a price of 12 pesos. 3 LEDs has a price of 10 pesos. One tack switch has a price of 11 pesos. One micro USB female to male has a price of 102 pesos. One battery holder has a price of 125 pesos. One RFP30N06 LEN channel MOSFET has a price of 70 pesos. So in total, the project costs 2,553 pesos.
In this chapter contains overall summary, conclusion, and recommendation of the study after the successful accomplishment of the project. The researcher initially sampled 15 for each type of coconut. Each coconut was knocked using a long knife and opened after. The results were used to development of knocking device. After acquiring the data, the researcher designed a system for knocking device. There were versions of fabricated device, each being better than the previous until the final version was achieved. This version had a longer life and stand alone. The device went through functionality testing. It was used for 45 random type of coconuts. The researcher gathers all the result and comparing for the accuracy of the device. As an conclusion, the device shows higher accuracy and it is indeed a great help to farmers and coconut vendors who does not have experience. It can also help for those consumers in choosing their preferred coconut type.
The next part of Chapter 5 is the conclusion part. After gathering data and reading the results, the proponents concluded the following. Considering the processes done by MATLAB in classification learner, Gaussian naive Bayes is the selected algorithm because it has the highest accuracy among the others. For the size of the device, it can be concluded that it is portable and power efficient since it is handheld and the measurement of the device is 14 cm by 7.5 cm by 15 cm. as well as it can operate for 16 hours. The classification of three types of coconut can be done by differentiating their peak frequencies. As the evidence, buko ranges 1,300 to 1,999 kHz, nyog ranges 2,000 to 2,699 kHz, and makapuno ranges 2,700 to 3,399 kHz. The device performs 93.3% of accuracy when random testing was conducted. With this, it can be concluded that the device can classify the three types of coconut. The device can predict any variants of coconut with no more than 2 to 3 seconds and has a training time of 1 to 2 seconds. For our conclusion of Chapter 5, the researchers successfully met the objectives of the project. The coconut classifier system has 93.33% of accuracy, can be handheld, can operate 16 hours, and can predict the type of coconut in just 2 to 3 seconds. Chapter 5 Recommendation. Through observation on implementation and testing of the system, the proponents of this study suggest adding a feature to the system that will automatically eliminate background noise when capturing the sound of the coconut. Secondly, to classify the nyog and makapuno without the need of dehusking the coconut. Thirdly, to add more samples of coconut for much higher accuracy. Lastly, to develop much smaller chassis for portability of the system. All the ideas mentioned above or earlier points to conclusion that coronavirus disease pandemic affected the outcome of the system. Resources became limited as it is difficult to find and acquire during pandemic, such as coconut samples and raw materials for the system. Furthermore, in-person group gathering of researchers and physical meeting with a coconut farmer also became a challenge to conduct testing, building the system, and other tasks which requires team cooperation. To sum up all the recommendation part of this study, the proponents are concerned on the area of the project about automatic elimination of background noise, classification without the need of dehusking, to add more coconut samples, and portability improvement. This is the end presentation of our group Coconut Classification System. Thank you all for listening.